Today's lecture we will discuss the supply systems. Supply systems, we mean transmission line, all the apparatus of transmission line, and the components of the supply system. Now, first of all, we will discuss what are the advantages of high voltage transmission. First one, it reduces the volume of conductor material, means it's reducing the cost of the conductor material. It increases the transmission efficiency. It decreases the percentage line drop. These are the main advantages of transmitting in high voltage. Now we have to prove each one of them mathematically. First of all, reducing volume of conductor material. If we consider a single phase line system or a single phase line transmission line, we have two major equations. First equation for the power equals to VI cosine phi, where cosine phi is the power factor, and W equals to I square R, okay, where W here is power losses per phase, okay, power losses per phase. Since we have a single phase, so we will have one W. P is the power transmitted per phase, V is the transmitted voltage, I is the load current. Now, if we substitute I into W equation, finding I here, finding I from this equation, and then from equation of the power, and then we substitute I here, we will get this equation. W equals to P square over V square cosine phi square multiplied by R. Now, we already know R, that resistance of any conductor, the resistance of any conductor equals to P, or equals to rho L over A, sorry. Resistance of any conductor equals to rho L over A, okay, where rho here is the resistivity of the conductor material, L is the length of the conductor material in meters, of course, and A is a cross-sectional area. Okay, now we substitute this equation in this equation, substituting equation for R in the equation for losses here. We will get W equals to P square or V square cosine phi square rho L over A. Now we are aiming to find an equation for the cross-section area of the conductor, which is A. Okay, so from here we get A equals to P square over V square cosine phi square multiplied by rho L over W. Okay, now volume of the conductor material, because we said that it reduces the volume of the conductor material. Now we need an equation for the volume of the conductor material. Volume of conductor material is multiplication of L by A, multiplication of the cross-section area of the conductor by the length of the line in meters. So volume of the conductor material will equals to P square L square rho over WV square cosine phi square. Now, from this equation, we know that the volume of the conductor will be reduced by increasing V here, by increasing the voltage. If we increase the voltage here, this equation, this value will be reduced by increasing V. This means that the relationship between volume of conductor material is inversely proportional with the transmitted voltage, is also inversely proportional with the power factor. Okay, so now we proved that transmitting in high voltage will reduce the volume of the conductor material. The second advantage, we said it increases the transmission efficiency. Okay, we know efficiency of any power system equals to output power over input power. Now, the equation for input power is transmitted power plus losses plus W. Here W, we already have W here. So losses are W. So input power will equal transmitted power plus losses. Okay. If we consider J to be the current density of the conductor, then A, cross-section area of the conductor material, is I over J, is the current transmitted through the conductor divided by the density, current density of the conductor. Now, the input power will equals to power, transmitted power plus V square over V square cosine phi square multiplied by rho L. A we have I over J. Now, because I here, then we will have inverse. We have to inverse this value. Now, I from the equation of power equals to P over V cosine phi. Let's substitute I here. We will get power equals to V square rho L. J is constant, we keep it here. V square cosine phi square is also constant, we keep it here. Multiply by I here. I is P over V cosine phi. Because it's in the denominator, so we have to inverse it. This is the value of 1 over I. Now, we have P is in common here, okay, and here. So this equation will be equal to P multiplied by, this is 1 plus, we take P from here, 1P from here with this P, J rho L over V square cosine phi square is going to be eliminated to this one over V cosine phi. So the final equation will be P multiplied by 1 plus J rho L over V cosine cosine phi here, because this is going to be eliminated with this square. Okay, this P is going to be eliminated with this one. So we will have 1P, this P plus P J rho L over V cosine phi. Now we take P common is here, P is common. So this new equation is going to be P multiplied by 1 plus J rho L over V cosine phi. So this is the final equation. Now, transmission efficiency equals to output power over input power. Okay, output power is P, or we can say output power, or even we can say transmitted power over input power. This is the value of input power. Okay, so P will be eliminated with this P. Final equation will be 1 over this value only. Now, if you simplify this equation, we will get transmission efficiency approximately equals to 1 minus J rho L over V cosine phi. So from this equation, if we increase V, it means we will reduce this value. If we reduce this value, it means minus 1 minus a smaller value equals to the transmission efficiency. So by this equation, we improve that the transmission efficiency is proportional relation with V, okay? Because rho and length and current density of the conductor material. These are constant values. Okay. The third advantage is decreasing percentage line drop. Now, line drop of any conductor equals to current, value of the current multiplied by resistance of that line. So, and we already know that the value of R can be calculated from rho L over A. So, line drop equation will equals to I multiplied by J rho L over I. Eliminating I with I will equals to J rho L. Now, percentage line drop equals to J rho L over V multiplied by 100. Okay, this is the percentage line drop. We see how many volts we have in the line as drops. Then we will divide them by the transmitted or by the source voltage, and we will get the percentage line drop by the transmitted voltage. If we increase the transmitted voltage, line drop will be less. Line drop will be less. Now, what are the disadvantages of high voltage transmission systems? First, they're increasing the cost of insulating the conductors, because if we increase the voltage, we have to have bigger insulators, and we have to have more distance among the conductors, because breakdown voltage will be higher. Okay. Also, it increases the cost of terminal of apparatus such as transformers, switch gears, and etc. Now we have to know what are the advantages of transmitting in high voltage, and we have to know how to prove each one of them mathematically. And also we have to know the disadvantage of high voltage transmission systems. Now, if we have to negotiate or differentiate among types of power transmission systems, we have generally two systems, either DC system or AC system. Each one of them is classified according to number of wires that we are using to transmit our power. First, let's consider our system is DC. We have either DC 2 wire, DC 2 wire with midpoint earth, or DC 3 wires. While in AC, we have single phase AC system, and then single phase is either 2 wire or 2 wire with midpoint earth, or we have single phase 3 wire. Then we have 2 phase, and then we have 3 phase. We have to understand how to differentiate among each one of them. In next lecture, we will complete comparison of conductor costs.